Hello everyone and welcome to yet another episode of Darko's Game Dev Cookbook. It's a pleasure to have you here again. Today we'll be talking about something super interesting. We'll be talking about parallax occlusion. It sounds cool and it is cool as well, so stay tuned. Welcome back people. It's been 2 weeks or 3 weeks, I'm not sure, since my last video, and I just built this cheater for fun one weekend and I said, well, why don't we just make it? Disclaimer for those of you who just stumbled upon this video or my channel, this video is gonna be a bit hard to follow for those people who don't have any experience with ray tracing or the stuff I did before here on this channel. For those of you who are here just to learn about parallax occlusion, how it works, I will cover the theoretical concepts as well, so you're on the right place. So feel free to stay and watch through the theoretical part. I would encourage you to try the code part as well, just for fun, and do something of your own and share it with me as well afterwards. It's super nice to see what people create sometimes. Super cool stuff. Okay, so as I said, we're gonna be doing this in 2 steps. First, I'm gonna explain some theory behind parallax occlusion in general, and then we're just gonna go into code. The code part, I'm gonna do it a bit differently than usually. We're not gonna build it from scratch or anything like that. That will be crazy to spend that time. We'll just use the code we built in the previous ray tracing tutorials. So we're gonna just use the whole ray tracing logic we built and just add the parallax logic to it. The thing you see right now on your screen that we're gonna be building is just a plane. So we're looking at that plane from above downwards. And we're gonna be using a cube map just to kind of get this slight reflection you see. But that's pretty much it. That's the basics. So let's first start with the theoretical part. Let the theoretical part jingle. Let's imagine that our surface, this is our surface. Or this is the surface on top, so we're looking towards this surface over here. We're looking at it from this angle over here, right? So this is our plane, and we can imagine that our plane actually has some sort of roughness to it, or it has some height to it. So the way this height will be stored, and you'll see in code what we're gonna do. We'll use a texture for it. Basically, it can be a grayscale texture of some kind, and the value of each pixel on that texture will actually tell you how high each of those is. So for this pixel over here, you will know, oh, it's 100. I don't know. In our case, it's gonna be normalized because we're gonna be using colors, so it will go from 0 to 1, and then each pixel will have some sort of a height to it. And you will know which point on the plane has which height, basically. That's what you're gonna figure out from this. So this is your eye looking towards this plane. At this point over here, we need to figure out what we need to see. So if you just had the texture, you would see this thing below, right? Because it would map like this. But we don't want to do that, right? We want to see the real hill, like in our crystal structure. In our crystal structure, if you look back into it, you'll see that the hills or the tops of this crystal structure occlude the things behind, so it is 3D, right? So we can go back to the drawing. What this algorithm does, it actually samples this thing. So this whole intersection, this whole thing will go from something to something, from 0 to 1, we can say, because our texture goes with values from 0 to 1, so this goes 0 for 1. In reality, you might want this to go from, I don't know, 0.3 to 0.7. It really depends what you want to do, right? You can scale that up and maybe make the range smaller depending on what kind of looks you want. But in our case, we'll just go 0 to 1. And the thing you do with this kind of mapping is that you will take a sample. So you will say somewhere in your code, you will say, take X samples in the direction you're heading towards. So I'm looking this direction, so take X samples, right? So you will take one sample here, 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 they will be of the same distance. So you would take the direction and then create these sample spots. And also, like, you can imagine that you're kind of digging through layers of terrain here. The reason why we need to do this is you really don't know when you're looking towards a certain point what you're gonna see. Like, there is no, you can't, I mean, in theory, this can be some sort of a weird quasi function you could intersect with possibly, but the simplest method is just to kind of take a sample and check, okay, on this sample, this height of this sample, is it below the value of the terrain, of the height of the terrain I have here, which is this range over here? Is it lower? No, it's not. Is this one lower than this one over here? No. Is this one lower? No, no, still not. This one, well, almost, but no, not really. And then you come to this over here and you say, oh yeah, I'm actually lower than the terrain height. So what you're gonna do in that case, you say, oh, I actually intersect with the terrain at this point over here, so I should probably take the value of this thingy over here, right? You can also, like, depending on what you want to do and what kind of coding you might be doing, because I really don't know, you might want to take either this sampled value, so you have some sort of granularity to your liking, or you can take the real terrain value, the color you get from that real pixel, right? Up to your choice. So let's imagine that you had the same, just to kind of give you a bit more perspective, that you have some sort of a terrain like this, and then you have your eye over here, and then you're looking here. What will happen now? Now you would get the occlusion magic, because you would get, when measuring this sample over here, you would actually get the height being lower immediately, and you would immediately return and say, well, this is my height, which means that this mountain over here, this top, would occlude everything here. And that's what occlusion does. So if you look into our example that we have with our crystals, that's exactly what happens with them, because you can see the tops of these occluding the things behind. And that's all. That's the magic. There is nothing more fancy than this. It's just pure math that we're going to be doing. Okay, now it's time to do some coding. I will be using a template. I will paste the template link down below in the description. You can use the same thing. You can also use this fork functionality to fork your own shader, or just copy and paste this whole chunk of code over here. All of this relies on the things we did before in the ray tracing tutorial series. Nothing is new. The scene I set up is basically a camera rotating around 0, 0, 0 at a certain distance and looking slightly downwards. You can also move it a bit up and down. You can tweak this however you want, really, but for this purpose, it serves the best, I think. So yeah, let's start. The first thing we're gonna be doing here, if you remember our good old intersect plane, we can return something here when we intersect with the plane, and we will get a color. So we get 1. There is this fonk shading function that I just copied from one of the examples we had. It also doesn't make much sense because some things are just global at the moment and we're passing them around, which we don't really need, but it doesn't matter for the sake of this tutorial. We can keep using it. Let me see. So we have this color that we're returning for the plane, but instead we want to return the texture. You can, in theory, you can use any texture you want here, but this specific one available here resonates well with the aspect of having height map, because it will mean that the white parts, or depending on how you define it really, but in our case the highest part will be this white one, and then as you go dark it goes deeper. It resonates quite well with this concept of height maps, and also we will use it as the base texture, so when you stitch that together it actually looks quite good. This one I put it here because you might want to add some noise to your crystals in the end, if you really want that, but it's not really mandatory. So we will first return pi channel 1, and we'll say p hit, because that's where we hit our plane, if you remember from the previous tutorials. And of course it needs to be RGB. I know from before that this texture itself has everything defined in the red channel. Let me see, what did I do? Of course p hit is 3-dimensional, and we're just we're focusing on the XZ plane at the moment, so you can just do XZ. And now you have this texture laid on this plane. So the plane itself, you're rotating the camera around this 0, 0, 0 and looking down towards the plane. So this is the thing you see. The thing you can also do, I don't know if I left it here, but you can do, since the texture itself is a bit more stretched than it should be for this example, we might scale it. Let's skip it for now, and we can do that later on. So the first thing we gotta figure out is how our parallax mapping algorithm will function. So usually when you're trying to figure this out, you would go like you would try different approaches and go back and forth a lot, which I won't do in this case. Usually what I did in this case, I first did bump mapping, that kind of highlighted the things I wanted in the correct way, and then I did the parallax component. So we might actually do something like that at this point, because it's important for you to also realize how we simulated the light in the end, because it's all fake. So bump mapping, what is that even? It's a technique that's also used to trick your eye into thinking that something is 3D and it's actually not. So if you have this plane over here, and then you have some light shooting at that plane in some way, you want to trick your eye to think that the texture that you have on this surface, that might be maybe a rocky surface of some kind, you won't trick your eye. So when you move around, or when the light moves around, you want to see some sort of a 3D movement. And the way you do it is that in bump mapping, you will have this texture over here. It will have some sort of a height map, the same as we have it with parallax mapping. Or it might also have, instead of the height map, so you need to calculate the normals on your own, it might have a normal map. Normal map would enable you to calculate this directly without this step we're going to be doing now. So we're going to be using a height map, and then using that height map, we can calculate not shadows, but we can calculate how the light interacts with our terrain. Bump mapping has one big drawback. So if you go like this, and then when you look at this surface from this angle, it doesn't even need to be super flat. It can be something like this. You will already notice when you go down, you'll notice that it doesn't look 3D anymore. You'll notice that something is off, because obviously you have a flat area. It's gonna look the same as we have currently in shaded toy, but the light will interact with it to some extent. So with parallax mapping, you kind of solve that thing, because you will actually see the real three-dimensionality of this terrain over here, right? How does it all work with textures and the height map? So in our case, we have a texture. In our case, we have like a bunch of these pebbles, right? That looked weird, and they're differently colored and such. It doesn't really matter. They represent, as we said, this texture is good because it can be used both as a texture, but it can also be used as a height map, because it has this granular change that you just saw in shaded toy. So if you look into this texture over here in channel 1, you see that the change is granular. So that's what gives us the power to actually use it as the height map. So if we go back to our thing over here, you can imagine the bump mapping technique as picking a point somewhere on this texture. Let's say we pick this point, and now let's say we extend this whole thing. So we zoom in, and we have something like this. We have this pebble. We take this point over here. What we do, and we can zoom even more actually. like this. What we do with this technique is that we take this point over here, we sample the height of it based on, of course, the color that we have on this texture. Then we go down, or you go two directions. You can go down and then right. You can choose any direction to your liking. To be frank, it doesn't really matter. The idea is that you go with 90-degree angle. So you go here, and then you need to sample this point and this point over here. This distance you have over here is something that will make configurable, like some sort of a resolution that will enable you to actually tweak how far you go to calculate the normal. And there's usually a sweet spot after which you don't see any difference. If you want to make your surface look super rough, so it actually tracks the subtle texture changes, then you will definitely go with something super small that you'll see in just a moment. So what happens when you sample these? You will get this height and get this height. So you would end up, if you look at this thing from the side. So if you imagine that your pebble is lying flat and this is your thing. If you imagine that your pebble actually, based on the texture color, has some height to it depending on the color. If you sample this one and then you got the height of this point over here and then this point over here, you get these three-dimensional vectors. And the key here is that once you get the two of them, you can do a cross product to get the normal that goes upwards. And you do that for all of these points on this thing over here. So you would go pixel by pixel as you usually do and just calculate normals for them, and then based on that normal you will actually get the lightning, right? So that's the gist of it. Okay, now we explained the map mapping, time to do some coding. We're gonna go through it quite fast, so let's go. We're gonna define resolution over here. That's gonna be our configurable resolution of sampling. So when you go down, when you go right, you're gonna go by this amount. You will be able to tweak this to your liking however you want. Of course, the lower you go, the more roughness you're gonna get, because the sampling is much denser. So the thing we gotta do here to be able to get these normals, we gotta calculate the right and down normal. So we're gonna say vec3 down equals something. P hit is the point where we hit the plane, you know, from previous tutorials. So this is the point where we hit the plane. So we need to move from that point in a certain direction. If we go down, that means that we go vec3 something. Bonus points for those of you who know exactly what to write here. The catch you gotta know here is that we're looking at a plane that's positioned in the on the XZ plane, meaning that the plane itself, the way we're walking along this texture, we need to change the X and Z coordinate to walk right or to walk downwards. So in the case of down, we actually need to ignore X, ignore Y, and walk along the Z plane. And by looking into this code, you'll quickly realize that the camera is at minus 0.3. Everything in front of it is getting more positive. So we can just go, if you're going downwards, we can just do minus resolution. That goes down. The other thing that you got to think about is that now this vector itself, it is not the vector itself, it is a point in space that is moved downwards from the point where we hit the plane. We need to get the height of that point, because right now it is going to have the value of y the same as the plane itself. The plane is positioned at minus 0.3, meaning that any point you hit on this plane will have minus 0.3, and we need to get the height. That's important to get the normal, because we want to get those two vectors, right? You want to get them three-dimensional, and the only way of doing that is that you actually apply some height here. So we got to calculate the y coordinate of down, and we need to write something like down.y equals something. And now we gotta sample the texture itself. So we're gonna write the function called get depth. So we're gonna do the inverse. We're not gonna search for height. We're gonna search for depth, because the parallax algorithm we're gonna be doing makes more sense when you work with depth. That's what you're looking for all the time. I mean, you can also invert it and search for height. It doesn't really matter. We might invert it along the way, actually. So we're gonna write vector2 coordinate of some kind. So you gotta sample the texture to get the depth of a certain point. So you're gonna return texture I channel 1 coordinates, and we're gonna return the red channel. And since we're searching for depth, we can do 1 minus this. Of course, just comment this out, and then also we can add something like scale, which is going to help us if you want to have higher mountains, or just normalize the lowest and highest point between different numbers than 0 and 1, because in this case the texture values will go from 0 to 1. Then you can use the scale argument to kind of just quickly configure it. Oh yeah, this is caps, so we're gonna do this. That's gonna get your depth. So down y is gonna be get depth of down xz. So we're just searching for xz coordinates to get the texture values. Then we have vec3 right equals p hit plus vec3 1. Not really 1, resolution. Then y is going to be 0 and z is going to be 0. Then we're going to write right dot y equals, so we're going to do the same thing as we had here. We're going to do right x z. Cool, and this gets us some things, but you gotta bear in mind that these are points. These are not the vectors we want to have. This is a point in 3D space that has x and z from this thingy, so moved p hit, and then y, that's the height. We gotta get the real vector that comes from p hit to this point. So down, we can just keep reusing this down, why not, is actually down minus p hit, and that's the general direction of it, so you don't even need to have any sort of length to it, so you can just normalize it. And then right equals normalize right minus p hit. So you get those two vectors by doing this. And now we do magic. Cross product. If you're not familiar with cross product as a concept in general, I will make a separate video just covering cross product, as I did with the dot product. Like, we're gonna do the math part of it, but in general, what cross product does, if you provide it with two vectors, the result is gonna be a vector that is perpendicular to both of those vectors. So if you have two vectors going some way and two vectors are always lying on a plane of some kind, right? You're gonna get the vector that's gonna be perpendicular, and it's gonna be in this case it's gonna resemble the normal of the plane they lie on. This is the way you get this magical normal out of these. So you have down, you have right, so they have some sort of position in place depending on, of course, the heights they just sampled. Yeah, one more important thing in this case, p hit doesn't have any y value that is actually worth caring about, because it's just the plane height. So we need to do this as well, just get the right values out. Let's see, p hit xz. Cool, so we're gonna get these perpendicular vectors. Another thing you need to know before you're doing a cross product, first thing you can do vector 3 normal equals cross down right. So you do this, and then you say normal. Cool. It looks quite trippy. It does something and it works fine. Usually a lot of people that I noticed when they're doing cross product, they just try it and see if it doesn't work. They swap these two. Obviously, if I did this, you would get inverted, the inverted picture, because it's gonna get the order matters. It depends. So when you look at the plane, it has two potential normals, right? One goes upwards and one goes downwards. Same with these two vectors. When you're calculating the cross product, one product of that goes upwards and one downwards, depending on the order of the cross product operation. What you use in this case, you use a so-called right hand rule. So you place your hand like this, basically 90-degree angle between your index and middle finger, and your thumb goes another 90 degrees. So what you do is that the first operand of cross product is your index, the second is your middle finger, and then depending on how you place them in world while you're looking at your hand, the thumb will represent the product of those two. So in your case, if you imagine, just like go through this cross product, we're doing down. Okay, what is down? You turn your hand towards you, you're like, oh, this is down. And then you look at your middle finger, that's right? It's pointing right, awesome. Where is your thumb? Your thumb is pointing upwards, which means that you're doing the right thing, because you want to get the normal that points out of the surface. And that's the trick you actually use to know without guessing too much. Sometimes you don't have the luxury to kind of test it out, because maybe it's not easy to just return it like this here. Maybe you need to do more calculations. So that's a really, really handy pun intended thing to do. So we return this normal over here. Also, let me see, this should also make a difference, so we can normalize it is a normal in the end, so we normalize it, and these are the normals that are generated based on your texture, and now you can increase the resolution, and then you get some slightly different behavior. The texture itself has slight variations to it, and this is it. You can see it much better now when you look into this, but this looks okay, right? So it's kind of blurry. We want to have this soft look. So right now we have normal, and then maybe instead of returning the normal itself, let's do dot normal. We have our point light defined globally here that we can just keep on using. So we're gonna do light. It's a point light, so we're gonna need to calculate the direction on the fly. So we can do, let me see, light there equals let me see, so this normal is at the p hit position, so we can in theory do this, p hit minus light position, and that we can normalize that. So is the normal that comes from the light to our little point, and then we can do a dot product between normal and light there. And of course, since we're returning a color, we can do this. It looks kind of neat, to be frank. And to make it even better, we can, before we ray trace this here, and I already did some magic before rotation over here, since we're not playing, and we can play, you can see what sort of a thing is happening. So you can see that the light is shining, it looks quite metallic, it looks cool, and this is just bump mapping. So let me kill this constraint over here that I placed before. This is just for fun. Let me kill this one as well, maybe -2, so we can do this. It also looks quite horrible if you look downwards. It's fine. We didn't do much to actually do anything about the looks of this scene. And then let's try doing this. Let's go with the camera. Let's go downwards. Let me see. We're doing something weird. Oh yeah, the position itself is definitely is definitely just based on the rotation function that we have over here. So we don't even need to bother with this, but what we can do, instead of bringing the camera down, we can just bring the plane up. And if you go even further, you realize quite soon that it's not as cool as it looks when you look at it from above. So that's just the thing I wanted to show you, because when you look at it from above, it actually looks 3D, right? Okay, the next step would be to introduce parallax effects to this one. But also what you can do right now, you can also play with the scale a bit. So you can do, it won't do much. It will just kind of stretch your current specter of heights. So it won't do much, especially in bump mapping, but you'll see, and that's where this is the place where also bump mapping show its constraints. You can't have, like, even if you're looking at it from above, if certain points are super higher than others, it becomes obvious that something is off at some point. It just needs to start occluding the things behind, and it doesn't do that. It just, well, it looks weird. Okay, so the next step is parallax occlusion. Let's go. Let's dive straight into it. To reiterate, what do we need to do? So now we have this parallax mapping thingy happening, or sorry, we have this bump mapping happening. Bump mapping fakes the light quite well for us, so it does look okay when you look at it from above. But we want to make sure that it also looks good if you go downwards, and that you have this occlusion happening as well. That's the key of this tutorial. So what we gotta do, or what we're doing right now, we actually sample a point, or actually let's make a bit different angle over here. So we sample this point over here. This point over here we call, in our code, we call it P hit. In our case, P hit has only two coordinates that are important. Those are X and Z coordinates, because it's a plane that lies in this on this XZ plane right now. We take those X and Z coordinates, and then we sample the texture itself to get the height on that point. So we just kind of go down, get this height over here, and we also then sample. Based on that, we create these normals. So we're going to create a bunch of normals so we can fake the light. So that's what we got with bump mapping. But what happens now when you need to have this occlusion? As I said in the theory part of the tutorial, you have a bunch of layers that you gotta create and sample. So what we're gonna do now, we're just gonna take this direction and go and drill straight to the bottom, up to the full depth. The depth in our case now goes from 0 to 1. And of course, with the scale parameter that I mentioned already, we will be able to expand this or shrink this interval if needed. So what we're going to do, we're going to do a simple for loop and then expand on this direction and kind of just keep drilling until we reach the point at which the terrain is above us. And we're going to say, okay, this is the point. It's kind of doing ray tracing with a terrain that doesn't have any, in this case, it doesn't have any regular function or anything we could trace against, but we do some sort of a quite dumb but smart way of actually brute forcing the height out. So we say here, oh, this is below, which means at this point over here, I want to display this height. Of course, as you can see, like if your resolution is not high enough, you will see slight issues. And of course, this will be quite a good approximation in the end. If you increase the number of layers, you do increase the accuracy of the thing you're displaying, but obviously at the cost of the performance, you lose in the end. So it's usually, you'll probably just tweak it until it looks good. And what you can also do, depending on the angle, you might increase number of layers you drill. For example, if you're looking at the thing straight from the top, there's not really too much need to do a lot of layers, because you don't see it from the side. You don't see the parallax effect of it. You just see it from the top. So maybe you could reduce the number of layers in this case. But yeah, for simplicity, let's just keep the static number of layers for now, and then we might iterate on this later on. Let's go to code. So where did we stop? We stopped at this point where, yeah, we need to fill in this get parallax function. I now also realize that I left when I rolled the code back for you to get this template code out. I left some things that I programmed slightly differently, so we can kick out this scale argument from ray trace, also meaning that you can kick it out from here, and you can kick it out from the parallax function signature as well. I'll make sure that the template code you actually have doesn't have these in, so don't worry about that. Here we're just gonna do our implementation, so we're gonna drill into the terrain, and we might define something like define layer count. We're gonna set it to 100 over here, and here we're gonna say so we need to calculate how thick each layer is to actually go through the loop and then kind of bounce down. So we're gonna say that the thickness of our layer, or height of our layer, is equal to 1, which is like the full height times scale, because obviously the scale you define will affect this specter of values you can have, right? And then you divide it by layer count, which will give you the number of the total number. You can put it to constant as well. It's not going to change at this point. And that will give you the height, the thickness of a single layer. Let me see what I did here. Yeah, of course, this is a float. So we need to cast this layer count, which is implicitly defined as an integer by the define up there. So we have some sort of layer height. Now we got to do some looping. So we're going to start setting up our main loop. So we're going to say for int I equals 0. We're going to start at 0, so at the surface of the plane, and then we're going to drill to the whole depth or thickness of this terrain, right? So we're going to say I equals 0. I is less than, yeah, actually it's going to be less than layer count, right? So we need to go layer by layer, and then we say I plus plus. And then here we're just going to go drill deeper from the point. So as I said before, this p hit you see over here, that's the point where you hit the sphere, right? And the x and z component of this matter, because that's the coordinates you use to sample the texture. The y coordinate is currently quite dumb, so it doesn't do anything, and it's actually just at minus 0.3 or something, depending on where our plane is. And the whole idea of this parallax function over here is to fill that space in. We need to know, we need to displace this p hit point. It will change the x and z coordinate as well, because we're going to be hitting a different point on the plane than before, but then we'll also sample the height at that point, and then we're going to get the real y coordinate. You'll see in just a moment. So we can say, so we got to return some sort of a point out when we pass this p hit. We need to dislocate it. So we're going to say vec3 new point equals p hit to start with, right? Because we want to return a dislocated p hit, and then we can return just new point. Or in this case, you can actually return p hit. It doesn't matter, because we're going to be returning a new point from this loop. And here we come to the interesting part. So we need to drill from, as I said in the drawing, we need to drill from this p hit position downwards, and we go in the direction we're looking at. So if you go back to code, we take the p hit. So we're going to say that we're going to have some sort of a sample point, which is going to be the point in this iteration where we sampled. And then here we say, well, it's p hit, but it's actually moving in the direction we're pointing towards or looking towards. And we're moving by a certain amount, which is going to be our layer height. This is again, this is an approximation, because some of you might already realize that the layer height depends on the full width of the terrain, and then and we're going using an angle, but it doesn't really matter at this point. It's gonna be good enough. So we're gonna go direction times layer height times, we're gonna cast I to float, because all of these are floats. So we move that p hit in the direction by a certain height. Cool. Now when we have the point, we actually need to see what the depth of terrain at that point is. So we're gonna say sample depth equals get depth at this sample point, and we only care about the x and z because the y is the height itself, and we're trying to get the height or the depth in this case, so we can just safely ignore it. And once you've sampled the height, you actually can compare stuff. So we have the sample height, so we're gonna say here if this sample depth, if this sample depth is larger, or actually if the layer depth is larger than the sample depth. So if you go back to the picture I drew over here, we need to find this point where our sample or our layer depth is higher, because the depth is going to be measured from the surface downwards. If it's higher or than the sample depth, then we break out of the loop and we say, well, this is our final thing. So if you go back here, you say, well, our layer sample height is, first we need to calculate that, because obviously we don't have it right here, but we do kind of implicitly already calculate it over here. So we're gonna say that the layer depth, I'm calling it height, I will change that. We're gonna say that the layer see, something is off here, yeah. Layer depth, current layer depth equals layer depth times float I, because that's the layer we're currently in, like this. And then here we can just use the current layer depth. And then over here we can do the comparison, because we have the current layer depth. So if our current layer depth is higher, so we want deeper than the sample, then we can create a new point for our p hit that's now dislocated and just return that instead. So we can have new point equals sample point. That's where we're sampling, but the sample point doesn't have the correct height. You can use this without correcting this, but you will have some sort of steps in heights you don't want to have. So you can just write new point dot y equals get depth, or sorry, we have the sample depth already, so we can just do this and we just return new point. Okay, we have this simple thingy all written, and of course this is sample depth. So if you're still confused by this, don't worry. Just go through this once more and go through the theory once more real quick, and you'll just realize it's not that complicated as it might look like. So we go back over here. Here we kind of forced the height of the p hit on this plane. We forced it to be the sampled height, so we might want to not do that. Instead of doing that, we want to get the parallax p hit. So we're gonna say that p hit equals get parallax p hit, and then we have direction. And wow, something is happening, right? You can see that the heights affected the normals we calculate using our bump mapping, and you actually see real stuff now. If I increase the number of layers, it of course affects the final render quite drastically, so you can get it quite smooth. But now if I play it, yeah, actually performance is quite okay right now, so it's not a huge issue, but I will leave it at 150. We really don't need it to be any better at this point. And what's left to do? Well, there's tiny details we gotta think about over here when we're sampling these things. In theory, I mean, when you get this P hit and you move in certain directions, we kind of linearly move now, and we might want to move using this get parallax function called instead, but we can leave it like this. I think the approximation is good enough for now. So right now, instead of getting this just normal and light there calculation, we can ditch that, and instead of doing that, we can calculate the lit position using Fonk shading that we have over here. So we can say vec3 lit color equals let's see, get lit color, and then we have a bunch of arguments to pass. So if you check the function signature, I'm just gonna copy it real quick so I see it. Like this. So we have view direction, we have direction, surface point position, P hit, it's the new P hit. Then we have object color, which is going to be, in our case, it's going to be the color of we need to get from the texture. So for now, we're going to type color, and then we're going to fix that in just a second. And then we have point light, which is going to be our light that we have. So we're going to pass light, and then we need to pass surface normal, and surface normal is going to be yeah, I commented out this part, which I should just keep, so we can do normal, and then plane dot material, because it's in the end of the day that plane. And of course I have some issues over here, because the lit color depends, like it relies on having some sort of a base color of the texture or the object you're trying to draw. So we can do text color, like texture color. I'm gonna say texture I channel 1. Also, let's kick this thing out. I don't think we're gonna be using it. I channel 1. We're gonna say P hit XZ. We're gonna use the R channel. What did I do? Yeah, of course, I need to kill this one. And I also placed this comma over here. And now we can use text color over here. Of course, yeah. So right now we have a lit color, we have text color, like the texture color. Let's try returning a lit color which relies on text color. So cool, we have something happening, right? You can see that the surface kind of reacts to light. Like you can see some specular components lighting up much more than the rest of the structure. Of course, if you look up, you'll see that it doesn't look great because the pattern is quite repeating itself. That's why I kept the camera down, because it looked cool. Among other things that look cool is that if you do some sort of scaling, you'll quickly realize that you can even do these sort of things animated. So you can make a sinus wave and it bounces. You can make it work with music. There's so many things you can do, but you can also make it look more like some sort of rocky beach or extra like some sort of ET planet. That's all up to you. So for example, you can call this scene Seaside Rocks, you know. It looks kind of wet because the material is defined like that. So I leave this to you to play, but my magical combination for getting these crystal looking structure was this one. Yeah, I also realized that the I'm getting the text color here, and my crystals had some sort of a color to it, so I'm gonna multiply it with a blue texture. I'm just gonna write it over so we have the right and proper numbers. Okay, let me see, times 1.3 times, that's the text color. Cool. And now we need to do some more magic. So as I said before, we have this cube map here, and the main reason for having this, yeah, I also realized that it might be a bit too blue, so we're gonna make it greenish. So now you recognize this, right? It looks quite familiar. It is the scene, almost the scene that we need to make. We're gonna kill this part here, and we're gonna kill this part over here. We don't need that code. And here we just need to wrap up our scene with some sweet reflections. So you already learned from me how reflections work in one of the previous tutorials. So we're gonna do that same logic we did before. We have the normal of the surface, right? And we're just gonna bounce that normal to the cube map. So what I can say here is that the color that we get reflecting is this one. So we reflect direction against normal, and that's gonna be our reflected ray, but we're gonna do texture channel 0 reflect, and this one, let me see, channel of course RGB. So we got some reflected color. Let's try doing this. This is gonna look cool. It looks like Terminator, Terminator 2, I think. It looks like it's gonna become liquid at any point, and now you can start playing with scale. You can get all sorts of interesting things over here. So, and scenes that don't resemble each other at all. You can iterate on it. And then we can take this reflected color and we can make something called final color, and it's gonna be a mixture of lit color and reflected color, and the mixture is gonna depend on, maybe we can take, since we copied this code from previous tutorials, the material we're using has something called reflection, so we can do material.reflection. This doesn't do much in terms of cleanliness of the code, because in the end of the day the code is not super clean already, but yeah, I mean, you can hook it up however you want, and then we can return final color over here, final color, and boom, you have your crystal looking structure that actually returns a pretty reflective surface. So you might want to decrease that depending on what you like, but I didn't put it super high, and voila, you have crystals. One thing, like I removed the second texture I had. You could, if you want, as a bonus task, you could possibly just add that texture in channel 2 and try to make this thing look a bit more rough. If you want to, also you can make it you can make it so that the light bounces from that texture. Depending on the texture roughness, you can make it bounce, diffract a bit differently, and reflect all over the place. So try doing that and see how it goes. I think it might be quite fun. That concludes today's tutorial. Now you know how parallax occlusion works, you know how to implement it, and that is awesome. If you liked the video you just saw, please do hit that like button. Also, if you like the content I'm creating in general, hit that subscribe button. It means a lot. Until the next time, see you.